over L. Okay, applied over here. Internal force diagram, how would that look like? In order to produce internal force diagram, it's called internal axial force. Yeah? So you consider this system, okay, this structure. If you take a cut, right, when you want internal force, you take a cut on structure. That is general things. Bending moment, internal force, you take a cut. So you cut wherever you want, okay, that point will be X. Okay. When you take a cut like so, okay, you cut here, then you want internal force, you just get this piece of force, okay, to calculate your internal axial force, alright? If you want to calculate based on the left hand side, you have the reaction force and then this distributed force, okay, take you more time. So you just end up with this. So F is the magnitude of distributed force over the length. If you integrate this F, alright, you end up with the force, okay? So this area represents the force that is acting on this cut, alright? Are you with me now? Let me know. No or yes? I am confusing for this yes and no. We are coming from different cultures. Okay, somebody yes like this, somebody yes like this, somebody no like this, and somebody no like this also. Okay, so can you do yes like this? Okay, so I understand it this way and no like this. So if you not, then okay, I understand that it is a yes. Feel free to raise your hand. Oh, sir, this is crazy. Give me another shot. Explain me another time. Just go ahead. Feel free. Okay. I don't want you to lose track of this course from this very beginning. All right. So please. Okay. If things gets too crazy now, okay. How come you get this one sort of thing like this? Okay. Please ask. But if you don't ask, then I understand that you understand. Okay. Don't be shy. Right. Because this is going to be your friends, okay? You're going to do something that could be more shyful in the future to your friends later. Something like you get drunk and crazy in front of your friends, okay, in the welcome party also, all right? That should be, you should be more shy in that situation than raising your hand in this class and ask. Hopefully you understand. Okay. If you don't ask, but please ask, okay, if something bothers you. So we integrate this area, okay, of the force distribution over the length, all right? What is it? Actually, you want to get force, right? So force come from, this is your bar, okay? So you need this force, axial force, okay, to balance with this force distribution, alright? So you need to get the distribution multiplied by dx, okay? The force intensity multiplied by dx, okay? Because this intensity is the force per unit length. So force per unit length multiplied by length, you get force. But this is the df, right? This df is equals to this f dx. Distribution multiplied by little infinitesimal length, you get little force that is contributed by this strip. So you integrate all of this from little strip here, little strip here, little strip here, little strip here, then you add up. This is an integration process, so you end up with F equals to integration of this distribution, which is this is fx. Okay, so fx over L dx. What you end up with? Fx squared over 2L. Okay. Fx squared over 2L. How does it look like? Simply just quadratic function. So your variation of internal force, internal axial force is varying like quadratic function. Here is your internal force distribution. So you have Fx squared over 2L. Okay, looks like this graph. At this point, 30,000 feet above the sea level, I kick you off into Atlantic Ocean. Will you swim back? You should be able to swim back right now. Right? I give you the distribution of the axial force. If you just divide it by the EA, you get strain. You get strain from this point if you don't swim back to the shoreline. I will just leave you to be like a food for sharks, okay, or some sort of sea animals, right? Okay, so divide by EA, you get strain distribution as a function of x. You get strain distribution, you integrate strain, you come up with displacement. So the delta is equals to 0 to L. Integration of this internal force Fx squared over 2L. This is force, so you need to change into strain by dividing by the EA, and then strain to the dx. Alright, integrate it up. So let's see, what was it? Why do we have, now we're gonna get an x cube, but should we have more L? Let me see. Oh, okay, that's right. Okay. So we have the Fx cube, right, over 3 to 2 LEA, evaluating from x being equal to 0 to L. This is your delta. So you end up with FL squared over 6EA. Done. What next? You come back to that condition again that the displacement has to cancel out completely. You come up with 0 at the support. So we have the FL squared over 6EA minus PL over EA equals to 0. Cancel, 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 cancel. Your P is equals to FL over 6. Okay, so this is FL over 6. What is your R? Your R is equals to how much? You integrate the whole thing, you come up with R. Alright, so to integrate the whole thing, you just take the area of the triangle, a half multiplied by F multiplied by L. So it is a FL over 2. So this side you have FL over 2, and then you have the FL over 6 into the opposite direction. a half minus 1/6, you get 2/3, right? 2/3, right? Huh? A half, which is 3/6, right? Minus 1, oh, okay, 1/3 of FL. FL over 2, and then FL over 6. Okay. Right. 3/6 minus 1/6, it is 2/6, 1/3. And then the other side, 1/6 FL. You add those two up, okay, 1/3 and 1/6, you add up, you get a half of FL, which is